Chapter 1 isn't extremely challenging or long, but at the end we do get into density and some little bit multi-step problems. And chemistry is about being able to think. So all the problems in this course are not going to be, okay, let me memorize how to do this. That's not going to get you through chemistry, or at least especially in a face-to-face class where you have live exams. Um, so uh, it's challenging to learn how to set up the problems because you really have to think about what you're doing. Okay. All right. So what do you think is the most important idea in all of human knowledge? Well, I'm sure there's some debate on that, right? But if you think about that scientifically, from a scientific standpoint, you can explain almost everything that happens in the physical world from chemistry, from breaking it down to molecules and atoms. And that's why chemistry is called the central science, because it's central to everything. And if you're going to be a chemistry major, or if you're pre-med, and by the way, I will say, if you're pre-health, it's very important for you to um, learn chemistry from the ground up, because you're going to be building on these very, very fundamental concepts all the way through biology, all the way through organic chemistry, all the way through biochemistry. So what you're learning here is going to take you through biochemistry, cell biology. I'm going to be talking in my medicinal chemistry class tomorrow about interactions that drugs have with the proteins in the body, which are called receptors or enzymes. And we're going to be talking about how those interactions are formed and what they look like, and that's coming back to atoms and molecules. So it really is the central science, and it really does determine how matter behaves. So an understanding of matter at the molecular level gives us unprecedented control over that matter, or at least the ability to understand it. And it even comes down to the way the human body works and biological systems work. So we all know that atoms are subatomic particles. You can't, submicroscopic particles. You can't see them, right? Generally, you can't see them with the naked eye. Um, Actually, some microscopes, which are called scanning tunneling microscopes, have been developed in recent years that actually allow us to see see atoms if they are in a crystalline structure, which is really, really amazing. And I have a video on that I might show later, or a link to a video. So free atoms are rare in nature. Most substances are in compounds. I'm going to talk about what compounds are a little bit in this chapter, and then more as we move on. And compounds exist usually in geometrical arrangements to form molecules. So here's an example of a molecule. We have here a water molecule, and the oxygen is denoted with a red sphere, and the hydrogen atoms are attached to that oxygen, and they are in white. Okay, so water is composed of, or uh, water in bulk is composed of these individual molecules of water that are discrete atoms that are made up of oxygen and hydrogen. So there's one oxygen and two hydrogens to every water molecule. Those are discrete molecules, and they all have that same form. Okay, and they all have the same orientation where it has this bent shape. And you're going to learn in this class, you're going to learn by the end of the semester, why is water bent? Uh, why does water have such a high boiling point, 100 degrees C, 212 Fahrenheit? You're going to learn a lot about the properties of matter according to the atoms that comprise that matter and the arrangement of those atoms. All right. So chemistry is a science that seeks to understand the behavior of matter by studying the atoms and molecules. So we see here that carbon can make up different types of structures. So here we have graphite on the left, which is pencil lead, and diamond on the right, which is just a different arrangement of carbon atoms. So just the way atoms are arranged can make the properties of that matter extremely different. So diamonds are obviously much harder than graphite. Pencil lead just breaks. I mean, and diamonds are one of the hardest substances we know. So you've probably studied the scientific approach before, and the scientific approach is important because if you're going to write a scientific paper, you need to use the scientific approach. You probably did an experiment as a middle schooler where you had to make a poster and you had to use the scientific approach for that. Okay, so it's based on observations and experiments. Okay, so key characteristics of the scientific method include observation, and from those observations, we're going to formulate hypotheses, and we're going to test our hypotheses with experiments, and then we will develop theories and laws. So observations are also known as data, or I think it would be better to say data is a type of observation. And observations are ways that we describe characteristics or behavior of matter. Okay. Even if you say, how much did it rain today? Well, we got 2 inches of rain. Well, that would be an observation, but you can measure that uh, property of matter, that rain that fell from the sky. You can measure it with a gauge, right? You can collect water and you can measure the depth of it. So Antoine Lavoisier noticed there was no change in the total mass of material within a container during combustion. So what he did was, let me find my pen here. So what he did was he put some oxygen and some fuel in a container. I don't know exactly what his experiment looked like, but let's say he had some fuel here and he had some oxygen gas in the container, and somehow or another he ignited it. Maybe he had a wire in there and he ignited it and burned up all the oxygen. He weighed it and he noticed the container didn't change in mass from the beginning to the end. This was in a closed container, and he noticed there was no change in mass. So that was an observation that he made, and from this he developed a hypothesis, and we're going to learn about that hypothesis that he made, and actually ended up leading to a law, and that's the law of the conservation of matter. So matter doesn't isn't created or destroyed; it just changes form. So if you think about it, why when you burn a log in the fireplace, it turns into a lump of ashes, right? So if it doesn't change, and obviously these ashes are a lot lighter than the log. So where did the rest of it go if that law is true? What do you think? You could put it in the chat. Got any ideas? Well, we're going to learn about that today. It actually went into the atmosphere. When solid fuels burn, organic fuels like wood tend to form carbon dioxide and water. And so it actually just was turned into gases. All right. And so Lavoisier explained his observations on combustion by hypothesizing that when a substance burns, it combines with components of air. A good hypothesis is falsifiable. In other words, we don't want something that we're only trying to prove. We also want to try to disprove our hypothesis in order to make it valid. We need a valid hypothesis. In order to have a valid hypothesis, it needs to be able to be disproven. So the law of conservation of mass states that in a chemical reaction, matter is neither created or destroyed, and that's what Lavoisier determined. So laws allow you to predict future observations. So a law is something that isn't debatable, right? Um, it was developed from hypotheses a long time ago. Laws generally were, and they're not debatable. They're always going to help you to predict future observations. Most laws are based on calculations as well. And you can test laws with experiments, but these laws again help us to predict how our experiments will come, what the outcome will be. A theory is a little bit different. A theory is a well-established hypothesis that's been tested over time and generally accepted to be true. The difference between a law and a theory is that laws always predict the outcome that the natural world will give us. Laws are not debatable. They're always going to be true. Theories are generally accepted to be true, but they're also falsifiable. I mean, they're also you can't always prove a theory. Okay, the a theory can always be disproven in some way or another, even if they're generally accepted to be true. All right. And so, for example, Dalton's atomic theory is one theory that explained what the atom looked like. And he did a lot of experiments to support his theory. It was a generally accepted theory for a long time, and it can explain a lot of the properties of atoms. But now we know a lot more about atoms, and Dalton's atomic theory falls short of all the information that we have today. So, theories are falsified or developed over time into more complex theories, or they can be expanded. But laws are not falsifiable. They're supported by usually by. It is muted. Maybe I hit some button or something. Very strange. Thank you for telling me. Okay, thank you. So, an observation. It was muted up there. I don't know how that happened. That was way over there. I must have hit some button on my keyboard. All right. So, an observation can lead to the development of a hypothesis. So, you'll make an observation and say, hey, I can hypothesize that this is going to happen. So, I think I can't really think of anything off the top of my head, but let's say um, I hypothesize that if I take a lump of sugar and I put it in this liquid, it's going to dissolve, right? Well, I can try that out. And if it does dissolve, I might further hypothesize that that liquid was water, right? But I could put some sugar into a liquid and it doesn't dissolve. And that it might look like water, it might be a clear liquid, but maybe it's not water. Maybe it's gasoline, and maybe the sugar doesn't dissolve very well in that. So that could be a type of hypothesis. And then if your hypothesis is supported by your observations, okay, so what you do is when you develop a hypothesis, you create experiments to test it, like I just talked about. So this sugar cube's going to dissolve in this liquid. So I'm going to take the sugar, I'm going to put it into the liquid. That's developing an experiment, right? And if my hypothesis is true, then I can call that a theory. I can develop a theory from that. Okay. And I can revise my theory with experiments. Okay. And if it turns out to not be true, okay, then I might want to revise my experiments some more, revise my theory some more, and develop it a little bit further. Or I might want to falsify my theory. I might want to say, hey, my theory's not true at all. I'm going to have to throw it out. Um, but from my hypothesis, I can also develop experiments and test those over. So, matter is anything that occupies space and has mass. So, your textbook, everything that you can see, everything that you can feel, it's all matter, right? Um, Matter is classified according to its state or its composition. Okay, so that would be its physical form, like solid, liquid, and gas, or its composition, meaning is it pure or is it a mixture? And we'll talk about that. So matter can be classified as a solid, a liquid, or a gas based on what properties it exhibits. And again, you've probably seen this before. The state of matter changes from solid to liquid to gas with increase in temperature. Now, that is not always true, and we're going to learn about that next semester. But Generally speaking, things go from a solid to a liquid to a gas. Now, some substances can go from a solid to a gas, and that's actually called sublimation. So, if you've heard of that, a sublimation printing process, which I actually have the system for, that means that the ink is going from a solid directly to a gas without passing through the liquid state. And some things don't go to a from a solid to a liquid to a gas. Sometimes they just decompose, right? So instead of melting, they'll just decompose. So this isn't always true, but in general, that's the way things work. So, like if you have water in the form of ice, if you heat it, it's generally going to go to a liquid in the form of liquid water and then to a gas in the form of steam. All right, and so here we have solid matter on the left, liquid matter in the middle, and gaseous matter on the right. Okay, and they all have different properties. Solid matter, atoms or molecules packed closely together in fixed locations. Okay, atoms and molecules are always moving because matter has energy. If it's above 0 Kelvin, and we're going to talk about what the Kelvin scale is, it has some energy. And so it's going to be moving even if it's just vibrating, but they don't move around past each other, and that's what makes them solid, giving them a fixed volume and a rigid shape. So, for example, at room temperature, we have aluminum would be a solid, right? And a diamond would be a solid. And below 0 degrees C, water is a solid in the form of ice, right? And solid matter may be crystalline or it may be amorphous. So diamonds are a crystalline solid. They have a repeating structure. They have a repeating order. Another crystalline solid that you may be familiar with is sodium chloride table salt. So sodium is Na and chloride is Cl. Okay, so we'll talk about these charges later on, so don't worry too much if you don't understand that. But sodium is positively charged and chlorine is negatively charged, kind of like the opposite poles, north and south pole on a magnet. And so they line up according to those charges in a repeating order. Okay. And so that gives sodium chloride its crystalline structure. That's why it kind of looks like little squares if you look at it up close. Okay. And in the next semester, we may study that. We don't get into that too much in this semester. Amorphous solids are like glass and plastic. They don't have a repeating structure. In liquid, atoms or molecules pack about as closely as they do in solids. So they're still very, very close together, but they're free to move relative to each other. They have more energy and they don't have a fixed shape. They have a fixed volume, but not a fixed shape. So if we go back to our little um, Erlenmeyer flask that had some liquid in it, it takes up the shape of its container, right? The liquid takes up the shape of the container. Water, alcohol, and gasoline are all liquids at room temperature. So again, this is temperature dependent. Gases take up a lot of space. They have a lot of space between the molecules and they're free to move relative to each other. And that's what makes gases compressible. That's why you don't want air in your brake lines, because if you're driving a car and you've got air in the brake lines, when you press on the brakes, it'll be mushy and it won't stop your car very well. So you want to make sure you don't have that. All right, so we can classify matter by its components. Matter can be classified according to its composition, elements, compounds, and mixtures. So if we have some matter, we can separate that into pure substances and mixtures. So does it have a variable composition? If it doesn't, then it's a pure substance, okay? So pure substances can be divided into elements or compounds. Elements, again, remember, free elements that are not connected together, that are not in molecules, don't generally exist in nature. But one example of one that does exist as a free element would be helium. Helium hangs around by itself and doesn't generally form molecules, and we're going to talk about why that is later in this chapter. But here we have an element, helium, right? It's represented on the periodic table as He. Or a pure substance can also be a compound. So like pure water. Here we have lots and lots of pure water molecules. They're discrete molecules, but that is a pure substance. The water is a compound, it's a pure substance. Okay. And if it has a variable composition, then it's a mixture. An example would be sugar water. Okay. That would be a homogeneous mixture, or something like tea. In water would be a homogeneous mixture, meaning that the molecules are evenly dispersed throughout and they don't settle out. That would be a homogeneous mixture. That's a solution, basically. A heterogeneous mixture would be something like wet sand. If you let it sit over time, it's going to maybe settle out. It can be separated fairly easily. Another example of a heterogeneous mixture, believe it or not, is a chocolate chip cookie. A chocolate chip cookie is a mixture, but it's got these chocolate chips stuck around in it. Okay, and so that's a heterogeneous mixture. A homogeneous mixture, believe it or not, would be something like a gold ring that isn't made out of, now a pure gold ring, that would be a pure substance, right? But most of our gold rings are alloys. So let's say we got 10-karat gold, it might have some tin or nickel or whatever else they put in gold rings. I'm not really sure, but an alloy would be a homogeneous mixture of metals. Okay, let's see. So again, we classify matter as a pure substance or a mixture. A pure substance is made up of only one component, okay? And a mixture is made up of more than one component. So pure substances can be elements or compounds, and mixtures can be homogeneous or heterogeneous, okay? So there are two types of pure substances, elements or compounds. An element cannot be chemically broken down into simpler substances. And I didn't think to bring a periodic table today. Those are the basic building blocks of matter. They're composed of a single type of atom like helium or maybe oxygen or maybe hydrogen. A compound is a substance composed of two or more elements in fixed, definite proportions. Most elements are chemically reactive and combine with other elements to form water, sugar, etc. Okay, so mixtures are categorized into heterogeneous or homogeneous. So remember, heterogeneous would be like sand and water. Homogeneous would be like that brass ring or tea with sugar in water. All right. So heterogeneous mixture again would be like salt and sand, and a homogeneous mixture would be like tea or sugar water or something like that. All right, so in these images, a blue circle represents an atom of one type of element, and a red square represents an atom of a second type of element. Which image is a pure substance, A, B, or C? What do you think? You want to type it in to the chat, A, B, or C? Pure substance. Correct. This A. A is the pure substance. Okay. And there are different ways to separate mixtures. Mixtures can be separated Um, well, in a lot of different ways. In fact, there's a whole science on separation science, how to get things separated. It can be extremely challenging to separate things. Um, a mixture of sand and water can be separated rather simply by decanting. So if you have some sand and water, say this is a beaker, you got your mixture here. So your sand's going to settle out on the bottom. You can just let it settle out and you can pour the liquid off. That's called decanting. And that's one way that you can separate a mixture. Or you could pour your mixture into a funnel with a filter paper in it, and you could collect the sand and the water would collect down at the bottom. So a couple of different ways to do that. But let's say you had that. Let's say you went to the beach and you got some water and some sand, okay? And you pour your sand and water through a filter, and you collect the sand here at the top and you collect the water down at the bottom. Now, do you have a pure substance, or B, in the beaker here, do you have a pure substance, or B, a mixture? Now, after you got the sand out, what do you got left? You went to the beach, you got some some beach water. Correct. It's a mixture because it's not a pure substance, it's salt water, right? You got to get the salt out of the water now. Now, how are you going to do that? So, this is a way that you would get the salt out. You could put your salt water over here and you would heat it until it boils. And when it boils, it becomes a vapor, and the vapor is collected in a tube called a condenser. And a water jacket is flows around the tube, not on the inside, around the outside of the tube, and the vapors are collected in the condenser and then they're collected over here. This is called distillation. Okay, we do this in organic chemistry all day long. We set up a distillation almost every week, sometimes two distillations a week, and that's to separate substances by getting the vapor collected over here. So you end up with pure water on the right and mostly salt or a more concentrated salt solution on the left, if that's what you're separating. And again, another way to separate things is filtration. You can use a funnel to separate, and you do that. If you make coffee, you kind of do this setup here. You're not really separating, you're kind of creating a mixture, but it's kind of the same thing, right? Let's see, it's 6:52. We can talk about physical and chemical changes. Physical changes are changes that alter only the state or appearance of a substance, but not its composition. Those are physical changes. The atoms or molecules that compose a substance do not change their identity during a physical change. In other words, like water, you do this all day long. You're going to boil your water if you make coffee or tea in the morning. Um, and it's still water, right? It didn't change from being water. That's a physical change. Or if you put your water into an ice tray and put it in the freezer and you make ice the old fashioned way, then that's still water. And if you let it melt, it becomes liquid water again. A chemical change alters the chemical state of the matter. So for example, if you take a nail and you set it out in the rain and the weather and it rusts, then it's going from being pure iron to being iron oxide or rust. So it's combining with the oxygen from the air to create a new substance. So in other words, we've got iron here combining with oxygen from the air to form a new compound, this Fe2O3. That's iron oxide. So rust is a chemical change, or burning a substance like propane is a chemical change. Let me blow this up a little bit here. So here we have some solid carbon dioxide, which is dry ice. It can evaporate and sublime actually and go into the gaseous state. That's a physical change. If you have solid sugar and you dissolve it in water, that's a physical change because you can just evaporate the water and get your sugar back out. But if you have a propane burner and you burn the propane in the presence of oxygen, I'm using my mouse here and that's not working too well. All right. Then you get carbon dioxide and water. That's a chemical change, right? So that's chemical change. So a physical property is a property that a substance displays without changing its composition. The smell of gasoline is a physical property. Odor, taste, color, appearance, melting point, boiling point, and density are all physical properties. A chemical property is a property that a substance displays only by changing its composition via a chemical change or chemical reaction. So gasoline burning, corrosiveness, um, uh, for like I don't know, like if you put acid on metal, it'll corrode it, stuff like that. The diagram on the left represents liquid water molecules in a pan. Which of the three diagrams best represents the water after they have been vaporized by boiling? A, B, or C? So we have people guessing different things. What do you think? A, B, or C? Maybe that was earlier. Well, actually, it's A. Okay, A is it's still water. See, this is H2O here. This is an oxygen and two hydrogens. Over here, the water has uh, turned into, let's say, oxygen and hydrogen. Right? You can do that through electrolysis. Or over here, it's been atomized even. So that takes a lot more energy. All right.